let's talk a little bit more about circles, in particular arcs that are created, that are part of a circumference of the circle, central angles, sectors, inscribed angles. Then we'll do a little bit more with radian measure. It's the measure of the size of the angle. So first of all, an arc is a part of a circle, and it is created by an angle that is formed from the center of the circle and 2 radii. So in red, I'm going to highlight the arc here that is created by this central angle. And say I had the letters A here and C here. Say the center of the circle was O. I would be able to name or call that arc AC, and that I would show that symbol over top. Later this semester, we're going to learn how to find the length of that arc, how to find the area of this piece of pie, and some reasons for doing that. A central angle is an angle that's formed at the center of the circle by 2 radii. So actually, I just had done that just a minute ago. So I'm going to draw 2 radii to form the central angle, and I'm going to name that angle AOC. So this is a central angle. This is supposed to be, the vertex is supposed to be right at the center of the circle. I had a little trouble putting it right at the center. A sector uses that central angle, and it bounds that and shades that area. Sector is a piece of pie is what it is, like pumpkin pie or apple pie. So I'm going to have eat a big piece of pie. I think I'm going to go back and do that again. So I'm going to draw that line straighter. So a sector is a region bounded by 2 radii. These 2 radii, bounded means included or enclosed by, kind of like a fence, and the arc that they intercept. So the sector that I'm trying to show you here, the piece of pie, pumpkin pie or apple pie, is that area right there, bounded by those 2 radii and the arc they intercept. Finally, I have a picture here of an inscribed angle, and I'm going to give it a name. So I'm going to call it ACB, and the vertex is right here. So an inscribed angle is one that's vertex set somewhere on the circumference of the circle, and it's just formed with a couple of secants. And actually, I don't know if you would call those secants because they don't extend this way, but lines that go through some part of the circumference of that very same circle. And there's a theorem about inscribed angles, and it says that the measure of an inscribed angle, that means the size of an inscribed angle, that looks to me, if I were to eyeball that, to be 40-some degrees maybe, is 1/2 of its intercepted arc. Well, see this arc right here? That's called AB. I'm going to write that down. That's arc AB. An arc can be described by the size of the central angle that creates it. And so the central angle that creates AB looks to me, this arc right here, looks to me, and I tried to make it to be 95 degrees. So this central angle is supposed to be 95 degrees. Therefore, this arc can be called 95 degrees. And this angle right here will be half of that one. So if this is 95, then angle ACB will be equal to 95 divided by 2, which I've got written down there, typed down there a little bit further, which is 47.5 degrees. Here's kind of a cool thing that you can do with this, and it kind of helps to see an inscribed angle. My line tool doesn't seem to be working. I might try it once and see what happens, but what I'm trying to draw is a perfect line right through the center of the circle. Yeah, that's not bad. So now what I'm going to do is, this arc would be called a 180-degree arc, because all the way around the circle is 360 degrees. So again, a 180-degree arc. These 2 radii, which make up 1 diameter, form that 180-degree arc. That means that any angle that rays that create it pass through this point and this point should be half of this 180 degrees. So I'm going to try to draw a straight line from here to anywhere. And I'm going to try it one more time and see if this will work. All right, that's not bad. And I wanted it to touch the circumference of the circle. Now I want to draw a line from here to here. Let's see if the tool will let me do it. And if I have done this and drawn this to be 180 degrees, then this inscribed angle should be half of that. Isn't that pretty interesting? I mean, that's like perfect 90-degree angle. I could do it again, and I'm going to try to do it now without using the line tool. So I'm going to draw a line right here, and then I'm going to draw a line right there. And I want you to see if that looks to be about 90 degrees because this is 180. That's kind of cool. This is almost starting to get a spirograph effect. So it's you've even drawn some pictures like this in your lifetime as a child, possibly. Okay, let's use the fact that the formula for the circumference of a circle is 2 pi r to decipher why, when we want to take an angle that's in degrees and turn it or convert it into radian measure. So in an effort to remind you one more time, I'm going to come on over here and I'm going to draw a circle. And I need to remind you that if I took the radius of this circle and put it around the circumference of the circle, that radii would go around 1, 2, 3, 4, 5, 6.28 times, or 2 times pi, 2 times 3.14. Yet going around that whole circle is going around 360 degrees. And what I want to do now is I want to convert from degrees to radian measure, which is a word based on the radius of the circle. So since 2 pi radii are equivalent to 360 degrees, I'm going to use a conversion factor. I'm going to divide both sides of this by 2. And I'm going to use the fact that pi is the same thing as 180 degrees. So if I came over here, right there, to 180 degrees, I'd have gone 1, 2, 3.14 times around the circle. So if I asked you to convert a 57-degree angle to radian measure, what you would do is you'd use the factor label method and you'd multiply that by pi over 180 degrees. And the reason that's the order you do that, that's because you want to get rid of those degree symbols and you want to have your answer in radians. If you would take your calculator now and go 57 times pi, you could hit enter if you'd like, and then divide by 180. You should get approximately 0.99, or we could even call it 1 radian. So 57 degrees, look at my picture over here, is about the size of that angle right there. And for a 57-degree angle, I can lay 1 radius around the circumference. So this is like stating the name of an angle. Normally we're used to seeing it in degrees. It's like changing feet to inches, or inches to yards, or meters to yards. It's just a conversion factor. It's a different way to name an angle. So next what I'd like to do is I'd like to convert 120 degrees. So would you just first notice with me that if this is about 60, then 120 degrees is about here, because here's 60, 120, and 180. So I think my answer should be 1, 2, and a little bit more. 1 radius, 2 radius, a little bit more. So I'm going to multiply by pi over 180 degrees. Would you do that, please, with your calculator? 120 times the pi key. You could hit enter, then divide by 180, and you should get the number 2.1. Remember how I said the answer should be about a little bit more than 2? It's 2.1 radians. We don't usually write the word radians, but I'm just getting you accustomed to this idea. And to convert from radians back to degrees, let's say I wanted to convert 5.4 radians back to an angle in degrees. Come on over here to my picture. 1 radian, 2 radians, 3 radians, 4, 5, about right there. That's where I want to go. So I want to know the size of this angle in a counterclockwise direction that goes all the way around to here. So right here is about 90 degrees. Here is 180. Here is 270 degrees. So this red line right here looks to me like it's about another 30 degrees over, so maybe about 300 degrees. In order to convert from radians to degrees, you have to do the upside down process. You have to put the pi down here because this is in radians and this is 3.14 radians. And you've got to put the 180 degrees up here. And so now, would you take 5.4 times 180? You could hit enter. Then divide by pi. You don't have to hit enter. So you could go 5.4 times 180 divided by pi, and you should get 309.4 degrees. We had estimated to be about 300 degrees, but we were awfully close. I'm going to really push this circle a little bit in Chapter 8. We're going to use it the most there. But if you would practice that in this homework, that would be very good.